Today we're going to look at the derivative, but today we're going to look at it as a rate of change. First time we looked at it as the slope of a tangent line, and we're going to ease our way into looking at in another way as a rate of change. Okay, these are some pictures that my girls drew, so I'll erase those in a minute. If we consider the slope of a line, which is kind of how we started, the difference quotient is the slope of a line. So if we think of just the slope of a line, the slope of a line is the change. If we think of it just basically, right, it's the rise over the run, or the change in the y values over the change in the x values. Y2 minus y1 over x2 minus x1, or f of x2 minus f of x1 over x2 minus x1. These all mean the same thing, and it's the change in the y value over the change in the x value. So together that gives us a rate, like how fast the line is increasing, how fast the line is decreasing. It's a rate. But this is called the average rate of change. This is known as the average rate of change of the y's with respect to x. That's what that is. The average rate of change of y with respect to x, or with respect to x. I might write it like that sometimes. That's a little abbreviation. Okay, so, and then when we took at these increments between x2 and x1 smaller and smaller so that there was almost no space, literally no space between them, that's when we add the limit as x2 approaches x1. And so that gave us a tangent line slope instead of just an average rate of change. Instead of an average slope, it gave us the instantaneous rate of change and a tangent line slope instead of a secant line slope. That's what we learned last time. So what that is also known as, the tangent line, when we added that little limit, we got the tangent line. When we add this limit, we get an instantaneous rate of change. So if we add the limit, we get not an average rate of change in general. If we add this limit, the limit as the delta x goes to 0 of the change in y over the change in x, we get an instantaneous rate of change. Okay. So today, which is known as f prime of x. So today we're looking at the derivative of a function as an instantaneous rate of change. And so to illustrate that in a nice way, we have the first example on your sheet. There's also a big thing that I've highlighted on your sheet. It's the definition of the derivative as an instantaneous rate of change, and it's in a little box. And basically it says when you add this limit to f of x, or this is how they have it written there. What's this? And then on the other side of that, they have the limit as x2 goes to x1 of f of x2 minus f of x1 over x2 minus x1 is f prime of x1. And that's the instantaneous rate of change. It's in a little box on your sheet. So now we're going to look at this example. But before we look at the example, there's just a few things to note. Here's a few things to note. About the derivative. This is just something to take note of. Number one, the derivative is a limit. It is a limit. The derivative is a tangent line, the slope of a tangent line. It's a slope of a tangent line. And the derivative is also a rate of change, as we're going to see today, the change in something. All right, so to illustrate this, what we're going to see is we're going to consider the distance formula, which you guys are familiar with. You've seen this for lots of math classes now. Distance is equal to rate times time, and this is where we have to say goodbye. If any of you guys watch JoJo, that anime. This is a little cartoon drawing of REO Speedwagon, or Speedwagon from that series. This is just how my daughter felt this morning. So anyway, there they go. Now we're going to look at the first example. And if you all are familiar with distance equals rate times time, because you've all ridden in a car, traveled somewhere, and you understand that if you get to drive fast, it doesn't take as long to get there. Or if you have to drive slow, it takes longer to get there. That is just the simple distance equals rate times time. So rate, R, is equal to the distance divided by time. You can easily make that transition with just a tiny bit of algebra. If we know that distance is equal to rate times time, then we know that the rate is equal to the distance over the time. Well, then we can talk about rate. We could use the word velocity instead of rate, and we can say, okay, velocity is equal to distance over time, okay? And we could say that, or basically distance, the change in distance, right? The change in distance over the change in time, how much distance you traveled over how much time it took. That's the average velocity, okay? And so sometimes instead of velocity, sometimes instead of rate, we'll use the word velocity, and sometimes instead of distance, instead of just traveling from here to there, we might use change in position. That way you could use it horizontally, or you could think of height, the height, change in height. So sometimes we just use this delta S. S stands for the position of a function. So the change in position with respect to time. Now, if we were to apply a limit like we did a minute ago, where we take smaller and smaller and smaller differences in time, so that it's not this far apart, we would take a little smaller and smaller and smaller distance in the time, it becomes an instantaneous moment in time, just like an instantaneous snapshot of the limit of the tangent of a function instead of the secant slope of a function. So that's what we're going to look at here, taking a limit, smaller and smaller and smaller increments in time. So here we go. On the first example that we have here, it says think of distance as height. Okay, the change in distance is going to be change in height, and velocity and rate as velocity in the example below. If a rock is thrown up on the planet Mars with a velocity of 10 meters per second, its height in meters t seconds later is given by this function. Y is equal to 10t minus 1.8 t squared. So what I'm going to first do is say y, I'm going to call it s of t, is equal to 10t minus 1.86 t squared. Okay, I'm going to just take note that t is in seconds, and that the height, s of t, is in meters. Is in meters. Okay, I just want to take note of the units right there. Okay, so it says find the average velocity over the given time interval. So they're not talking calculus, they're just talking the change in s over the change in t. So I've given you this chart to help us find our way through. So we have t, different values of t when t is at 1, and this is in seconds, right? When t is 1 second, 2 second, 1.5, 1.1, 1.01, 1.001. All right. What is the position after this much time has passed? So after 1 second, the position, the height is 8.14 meters. And so I found these values, but you should double check, because on the last video you guys found where I'd made an error. So just make sure I'm putting these in right. I got 12.56 meters. I got 10.815 meters. I got 8.749. I got 8.2036. I got 8.1463. Oh, these are all in meters. I don't have to write the M. We know that these are in meters. I'll just say this is in meters. So this is the distance after this much time has passed. Okay, so how I got these values very quickly in my calculator was I went to my y equals screen, I put in This formula right here, I went to second table, and like we talked about in the earlier video, I changed my independent variable from auto to ask, and then I told it what x values I wanted to know the y value for. So you can do that, get these values out real quick. Then, what we want to know is we want to calculate the average velocity for these different time spans. And so what are the time intervals? So here on your next little table, I tried to give you, okay, the time interval. So if you had to do a problem like this on your own, what would you do? You would do what we're doing, I'm leading you through now, is you would say, okay, what is the y value? What is the difference in the time intervals that I have to calculate? And so like, this is from t is 1 to t is 2 seconds. Then we want to look from t is 1 to 1.5. Then we want to look between t is 1 to 1.1, 1 to 1.01, and then 1 to 1.001. What are we looking at? These are not random values. What are we doing? We went between 1 and 2 seconds, then 1 and 1/2 seconds, 1 and 1.1, 1 and 1.01, 1 and 1.0001. We are shrinking the time from 1 whole second apart to 0.001 seconds apart. We are taking a limit as the change in time goes to 0. This is going to help us see an instantaneous rate of time at when t is 1 second. That's what we're figuring out, the instantaneous velocity when t is 1 second as we look at this. So how do we calculate that? Well, you got to know the change in s. So I just stepped us into this. I said, okay, for these time intervals, what is the change in s? Oh, no, first we'll say, what is the change in t? And then what is the change in s? And then we're going to calculate the change in s over the change in t, which is the average velocity. All right, that's what we're looking at. Okay, so what is the change in t? Well, this is just t2 minus t1. That means the difference in, the subtraction in. So 2 minus 1 is 1 second. 1.5 minus 1 is 0.5. This is going to be 0.1. This is going to be 0.01. This is going to be 0.001 seconds. This is in seconds, okay. Then, how can I find the change in s over the change? This is, what am I doing here? This is basically s of 2 minus s of 1. The position of the function after 2 seconds minus the position of the function after 1 second. This is why we did this chart. So now I'm just going to take 12.56 minus 8.14, and so what I got there is 4, oh no, did I even do it? I might have skipped this one. You might have to fill this in yourself. Let's see if I'm not sure. Let me see if I can find somewhere where I wrote that down on a different sheet. If I did, hang on. Here it is. Okay. Only I didn't make this table last time, so let me see if I can find some of these values. I said that this was 12.56 minus 8.14. Oh, I didn't write these values down. Okay, so you can fill in this part if you want, but let's just see. What are we going to do? We're going to take this divided by this to get this answer. We're going to take this number divided by 0.5 to get this answer. So this is basically s of 2 minus s of 1 over t2, which is 2 seconds minus 1 second. I'm going to put in the real numbers, but I want you to see what we're doing here. This is s of 1.5 minus s of 1 over 1.5 minus 1. This is s of 1.1 minus s of 1 over 1.1 minus 1, and so on. That's what I'm doing to calculate, and these are the values that you'd get out. Right here, you would get 4.42 meters per second. Here I got 5.35 meters per second. Here I got 6.09 meters per second. Here I got 6.3 meters per second. And here I got 6.3 meters per second. That's what I got when I took the time interval between the average velocity from 1 to 2 seconds is 4.42 meters per second. The average velocity between 1 and 1.5 seconds is 5.35. Between 1 and 1.1 is 6.09. Between 1 and 1.01 is 6.3, and between 1 and 1.001 is 6.3. It was increasing. So let's answer part B to this. It says estimate the instantaneous velocity when t is 1 we're getting closer and closer and closer to 1. And so I would say that the instantaneous velocity when t is equal to 1 is 6.3 meters per second. That's what we could say. So let's write this a little bit differently. What is this? What is this right here? Let's write it as a limit. I have it somewhere on there. Let's write it as a limit, I think right underneath there. As a limit, what would this read? Let me erase part of this so I can do the limit part. What would that say? It would say this. That means that the limit as t approaches 1 of the position of the function minus the position of the function of 1 as t of t minus 1, this is how I write it as a limit, is equal to 6.3 meters per second. This is the instantaneous velocity. This is what this means symbolically. This is equal to the derivative of s when t is 1 second. That's what that's equal to right there. So let's compare this to the definition of the derivative. The limit as x approaches a of f of x minus the function at the value a over x minus a. Our independent variable here was x, but here it was t. The value we're interested in instead of a was 1. It looks just like the definition of the derivative, which is equal to f prime of a. So that is another way that we can look at that derivative. Okay, let's go ahead and look at example 2. We're still using the same problem, but they're just asking us some questions. So let's answer these questions. It says, well, first let me make some room here. It says, it's the same example. A rock is thrown upward on the planet Mars with a velocity of 10 meters per second. Its height in meters after t seconds is given by this same equation right here. Okay, this is all the same setup, but now they want us to answer some questions, and let's just put them in words so we understand what things mean. Let's finish solving this. It says, what does s prime of t represent? S prime of t represent. Okay, let's see. S prime of t is the instantaneous velocity at t, at time t. That's what it is. This right here, S prime of t, I had just written it down. It's the limit as, we can think as, let me just see how I want to write this. We could do it as the difference quotient as h goes to 0 of s of t plus h minus s of t over h. This is one way we could write this. If we had a value that we were interested, like we were a minute ago, we could use the a definition where t approaches the number a. So this is what this is. It's the instantaneous velocity at time t. B, if s prime of t is equal to this, they just told us that. We didn't have to figure it out, but we could totally figure it out by using this definition. And you will have to do that actually on test 1. Find the velocity after 1 second. So what is the velocity of after 1 second? Well, since this represents the velocity, we're just going to plug in 1 for t right here. So to answer this question, we're going to take s prime of 1, which is 3.72 t. Did I flip a sign right there? No, I've missed the negative. Minus 3.72 times 1 plus 10, and that gives me 6.28 meters per second. So that is the velocity at 1 second. Find the velocity of the rock when t is a. Okay, what is the velocity when t is equal to a units? A seconds. Well, all we'd have to do to figure that, this is the velocity. So let's plug in a here. That would equal to s prime of a. That's what it would be. negative 3.72 times A plus 10. So if they said after 4 seconds, you plug in 4. After 3 seconds, you plug in 3. After A seconds, you plug in A. That's all that's saying. And the units are going to be in meters per second. It's always a change in meters over change in time. When will the rock hit the surface? This is not a derivative. When we're looking for time. Will the rock hit the surface? What is the position of something sitting on the ground? The height of that is 0. So to answer part D, all we do is we take the position function, S of t. Where is that? Oh, this is the position, right? This is the position. S prime of t is the velocity. We take the position, and we set it equal to 0, and we solve. Okay, let's solve this. I'm going to factor out a t. This is a quadratic equation, right? This factors very easily into t times 10 minus 1.86 times t equals to 0. To finish this, we would set each factor equal to 0 and solve. And right here we get when time is a 0. Okay, so it starts on the surface apparently. That's the first time it's on the ground. And then it's lifted up and launched from the ground is what this is indicating. And the second time it's on the ground is when t is equal to 5.4 seconds is what we get here. Okay, so answer to part D is when will the rock hit the surface? After 5.4 seconds. Part E, with what velocity will the rock hit the surface? This is asking what is velocity when t is 5.4. How do we find the velocity? We put it in the derivative. So to answer part E, we say, well, what is S prime of 5.4? And we plug that in. And we get negative 10.1 meters per second. Now, what does this negative indicate? Well, it indicates that the designation, something's going up and coming down, and you can even see that in this formula. This is a parabola, right? This is some parabola that's facing down because the leading coefficient is negative. What this is indicating is that up is designated to be a positive direction and down is designated to be a negative direction. And so this is going in the negative direction. That's what that negative is telling us right there. Okay, so that is the first two examples. I'm going to pause so that this video is not too long, and we're going to see part 2 of this.